I don't have my usual background. I'm not going to do um, as in-depth detail as we have in some of the last videos because we did a lot of really hands-on. Uh, got our hands dirty. Um, I just want to finish this train of thought because people asked about stocks, and here we are. We're ready to talk about it. So, let's hone in on and talk about stocks. Oh yeah, I don't have my usual Windows Note background. It's all different for the grand finale. Not of the series. I might keep going. So actually, before I get into it, well, one, as always, let me know if you want the details that I'm skipping in this video. But also, I mean, probably I'm going to pause for a while because I have more pressing issues than YouTube videos, like marking and trying to find a job and write my thesis. But um, where do you think I should go next? Some things I'm thinking about are so I work a bit with perverse sheaves. Um, so that's something that comes up. And maybe on the way to talking about that, I could talk about local systems and what those have to do with representations of the fundamental group, which sort of feeds into that. Um, I thought about possibly we could go to Topos theory, right? We could talk about topoi or toposes as you prefer, which is like a more general setting for sheaves that makes possible stuff like the étal topology. And oh my God, my computer's making noises. The étal topology, but then there's also sheaves in like logic and set theory and stuff that we could talk about. And I know maybe less about this, but this would be good motivation for me to learn more to explain more to you. And what else we could do? I mean, we could also just dive more directly into sheaves in say algebraic geometry, and like we could talk about you know quasi-coherent sheaves and like sheaf cohomology. So I don't know, let me know down below. uh but enough of me yapping. Let's get into um the main point of today's video. We're ready to talk to connect our hoity-toity understanding of limits to stocks, right? So you might recall that before we considered some diagram and um, you know uh, category. So these are just two categories, and we talked about our dressed up version of we had this diagonal functor, and we got adjoint. So the right adjoint, the one that we talked about last time, was this limit functor, but there's also a left adjoint, which is the other limit functor. I always forget which one's co or projective directed, blah blah blah. I remember, I don't know, the diagrams and what they do, but the notation, I don't know. I've got my notepad here and it always escapes me somehow. Um, right. And well, there's sort of there's universal properties that these satisfy, right? We found another way to write out these descriptions. So the one that we saw last time was the limit that points this way is some object together with a family. So it's an object, but it also gives you morphisms. So you need to specify what these arrows are. Um, that said, for any arrow going between, oh, you know what? I've not defined some notation here. So let me back up a second. We're trying to unpack this in more natural language. We're slowly working our way back down to earth, right? And before I get into that, let me say things this way. So we're going to consider the case where now we're going to consider a poset category. So what do I mean by that? Well, suppose that you just have some set J, right, or index. So now J is well, I'm gonna abuse notation a lot. So J is a set together with some partial order, and we're going to build a category out of it. So what are the objects of this category going to be? Well, so sometimes we read it ob J or maybe J naught. Well, those are just going to be the elements of J. And the morphisms of this category is, well, basically, if J is less than or equal to K, then I'm going to say that there's a unique map from J to K. And of course, it will be the case that, if J is equal to K, well, just J, then that one unique map is the special map that we call the identity on J, right? So in that way, right? So the I mean, basically, the only other thing we need to verify is that like we can compose morphisms, and that will give us a category. But that's just the transitive property of the partial order, right? So in this way, each poset gives us a category, and you can sort of go back from that category to poset. So just a different perspective. Okay. Well, now let's imagine that we had a functor from our poset into our category. Well, then if I define, say, a sub I to just be the image of I under this A, well, that gives me an indexed family, right? I just get some family indexed over J of objects in my category C. So okay, there's more to unpack from that functor, but basically a functor from a poset into our category is just, gives us on the level of objects, just on the indexed family of objects in our category. And also a special thing on the morphisms, right? It also tells us that we have a morphism phi ij from a sub I to a sub j whenever I is less than j. And also that phi I is the identity, and that phi k sub j precomposed with phi ki is phi ki. For whenever I is less than j is less than k, right? So actually, here is a sort of more down to earth, in a sense, description of this case, right? So if J happens to be this category corresponding to a poset, then we have all of these conditions, right? We get some indexed family of objects in our category, together with some maps between these things. So all of these claims just come from, unpacking, like supposing I is less than J, that means there's a morphism, apply the functor F, and all of these properties in the box fall out, right? But conversely, right, forget we even talked about like this category J in a more natural language. We might talk about just starting with some indexed family of objects and maps between them that satisfy these properties. And you recognize that, well, if you had an index family of objects with maps satisfying these properties, that's equivalent to this data, right? So well, we're asking that along with this indexing, we do have the pre-order, right? But then when you just go back and unravel exactly what these things mean, this is equivalent to supplying to taking your ordered set, your partially ordered set J, and supplying the functor that sends, I less than J to whatever this map is. And then again, you just unfurl the properties of like composability, right? If you assume this, that's exactly what makes this a functorial assignment on the level of the morphisms. Great. Okay. And so what we can do in this case, what I'm gonna do, so we have dark orange. Sure, why not dark orange? So now we've got these two kinds of limits, right? We've got there's one satisfying universal property here. So now I can make sense of this notation of this indexing of objects. Or I used subscripts, so maybe I'll go back to using subscripts over here. Right. So there's one that said, I've got here's there's some object. It's my limit. There's arrows down to both of these, and for any other object with arrows down to both of these, commuting with my maps, where here this would be phi kj. There's a unique morphism making this whole diagram commute. And then the other limit just satisfies, well, an upside down version of this, where now these would go up top. And now I have maps going into this instead. So this is the one we didn't talk about last video, but well, you can guess or look it up that everything works about the same. Great exercise to try and prove everything from the last video for these diagrams instead. And okay, but what I can do in this special notation, because if I didn't worry about all these adjointness with diagonal functor stuff, if I just had this data of some indexed family of objects and morphisms, what I'm going to do is I'm just going to define. So this is just like another piece of notation, the limit, over these objects of a sub j. If I write this, what I just mean is like the limit, this limit here, right? This is the special object I get coming out of this adjunction, right? And then a similar notation for this other limit as well. Great. Okay. So now what we're going to do is we're going to give this a concrete model. So suppose, right? So we've got J, we've got some ordered set, and we're going to suppose that this category that we're dealing with now is maybe like a subcategory of set, right? Of the category of sets. It could be set itself. I'm just framing it this way because, of course, a lot of the examples we care about are, things like abelian groups and modules and rings, right? So literally everything I'm about to say, I'm just going to talk about it in terms of sets. But then if you wanted it in terms of groups, abelian groups, modules, what have you, vector spaces, well, you just need to go and verify that all the maps I'm going to tell you about, of course, they're functions. You just need to convince yourself that in these scenarios, we would also get like homomorphisms of whatever objects out of it, right? So that's just a bit of extra work, but is, some fairly routine checking. And so in this case, I'm going to give you a concrete model for each of these objects. So it's going to turn out that the limit with the arrow pointing this way, you can always, I'll write, say, just up isomorphism. So this limit is the same thing. You could get it if you took just the disjoint union of your objects, well, now we're imagining their sets, and you take a specific quotient. And what is that quotient going to be? I'll tell you in a second. But just to jump ahead for a moment, a way to get a concrete model for your limit with the arrow pointing in the other way is this will be instead isomorphic to, or uh, maybe let me write it this way. So there'll be a injection into, well, let's think about what's the dual of a co-product, right? The dual of a union, of the quotient of a union. Well, that's going to be a sub, right? So sub is dual to quotient, and product is dual to union, right? So instead, we're going to get a sub. That's why I write injection, some subspace of the product, some subset. And then, of course, yeah, it'll be like subspace if it's a vector space or something. Okay, so what is this concrete? What is, well, this already almost tells you, right, how I'm going to build the concrete model, right? So I'm going to take some quotient, some equivalence relation. What is that equivalence relation going to be? Well, let me just remind you that what we're asking in the first scenario is that okay, I've got these. Ooh, wrong. Is that I've got these maps, right, from AI to AJ that satisfy this compatibility condition. So what I'm going to do is I'm going to glue all these sets together, right? I'm taking the disjoint union, and I'm going to say, well, if I had two elements in this disjoint union, A and B, so maybe A is in A sub J and B is in A sub K, right? Because of course, if you're in the disjoint union, you've got to live in at least one of these things. And I'm going to say that A is related to B if there exists a K, which is, or sorry, an L, which is both less than J and K, such that A, and we map into, right? Remember, we have a map because L is less than J by the above. I have this unique map from AL to AJ if these two maps agree. And that should start to be looking pretty familiar from what we talked about in terms of stalks and restriction maps, right? Um, yeah. And so that's basically it. That's basically it. That is how I build my concrete model. This defines, so I claim, again, if you ask me nicely, I can do the details, but I claim that this defines an equivalence relation and that this object here, well, in order to convince you that this really does give me a limit, right? I just need to show you that this satisfies this universal property. While technically I'm not quite done with the definition, right? I also need to tell you what these maps are going into my limit. Well, that's kind of clear though, right? If I have a J that gets included, right? I just take my inclusion into my disjoint union, and then I just take the quotient by the equivalence relation. Well, in other words, I'm sending an element A to its equivalence class. And there we go. Now we have in all of these situations, at least when our so-called diagram category is some partially ordered set, I have a concrete realization for my limits. Okay, so in particular, the example of our interest is when our category, our diagram category, is the category of open sets. Or rather, I suppose in this situation, technically what I want is to take opposite, right? because now I'm interested in sheaves, which are pre-sheaves, which are functors from here into, I don't know, I guess abelian groups technically, or we could even just imagine it's into set, right? And well, what's the order? Of course, it's just the order relation, right, on open sets. So U is uh, right less than or equal to V if U is a subset of V, right? So that's our diagram category, and our sets, these like A sub U, because now our right these sets are indexed by the open sets. Well, that is just going to be right the sections of my sheaf. And so what does that mean? What do I have for this concrete model, right, for my limit in this case? Well, this would be over all the I've done something a little bit foolish. We don't take this limit over all open sets. So maybe you've caught my mistake already. Um, we want to take we're imagining I want to take the stock at a particular x in x, right? So I get what I really want is the category or the poset of all open sets in here such that U contains X, right? So you can check that this will still give you, right? This will be a subset of our full set of open sets, but it will still give us a poset. And so this is what we want our J to be, with, of course, together with the subset property. Okay. And yeah, now, like I said before, the AU is going to be just our sections of the sheaf. And so our indexed family, all right, this is just our index family. I guess, I could write it U in J. And now if I go up, right, and I look at this whole definition of what we demanded on our indexed family, well, again, this is just like these would be supplied by the restriction maps, right? Whenever U is a subset of V, then I might have written things backwards. uh yeah, small typo there with the something's happening with the opposite, but like I said, this won't be the most precise of the videos because we did a lot of very precise ones recently. But the point is, when you unfurl all of these, what we get is that this does just become a family of objects with the restrictions on maps that we considered before. And that's basically it. So that is how we go from that is why this abstract categorical definition of limits in terms of universal properties ends up just becoming us taking this direct this union over all of these stalks or all of these sections over open sets containing X modulo this equivalence relation, because actually, if you just unpack this general recipe that I gave you for how to build limits, and I've given you enough information to prove that this, at least in the category of sets, will always give you a concrete description of this kind of limit. If you unpack it, you just get our original definition of the stock of a sheaf. So let me end on one last thing. I should tell you about I'm going to say a little bit more about the dual notion than I did last time. And so the dual notion would be if I had a family of maps that I now think of as projections, whenever I is less than j. And now, oh, did I write the arrows the wrong way again? I'm always writing arrows the wrong way. Oh no, this arrow, this arrow points to the right. Yeah, this arrow points left. Great, amazing. So now I want to give you a concrete description of this limit with the arrow pointing left, and I said it's going to be a subspace of the product. So what is that subspace going to be? Well, if I have some, so call this a sub j, right? This is just like an indexed collection of objects, right? Something in my product, a sub j. Well, you can imagine there's just going to be a similar compatibility condition, right? I'm going to say that it has to be the case that if I apply this projection to a sub j, that I get a sub I, and that should hold for all I less than or equal to j. So that's the restriction I take on my product. And then the map I'm going to get down to some AK is just going to be the projection on the kth factor, right? So I have my sequence of elements, a sub j, and I just the kth projection, right? Because remember, I need to tell you what these maps are here as well. And now we have them. And of course, the thing to check is that makes that diagram commute. Again, that's just a matter of the compatibility conditions we put on all of these maps. Right. So you have to be able to compose these whenever these make sense, right? A K to AJ to AI. So we should be able to go J I precomposed with K down to J is equal to pi of K down to I whenever I is less than or equal to J is less than or equal to K. And so a classic example of this is if we take the collection of objects being the integers mod p to the m, and I take as my projection map well, rather, I guess I should say more about how the indexing works. So my family of objects is going to be z mod p to the n, and whenever well, I guess just whenever uh, uh, m is greater than or equal to n, I get the projection map where I just take whatever my integer here is, and now I just go mod p to the n, right? And in this case, when we take the limit over all of these things, we get a ring. So you check, each of these are ring homomorphisms. And again, you can do this. This isn't special in this case, right? You can go back to the very particular case here, and you can see, if your limit happens to exist, and if all of these, I guess I should say, these morphisms, these pi happen to be ring morphisms, then you can convince yourself your final object is a ring. You just need to, check compatibilities on, well, in this case, it's maybe easier because you have got some subspace. You just need to check that it's closed. In the other case, you've got to check well-definedness on equivalence classes. But anyways, the resulting ring that you get is isomorphic as a ring to the p-adic integers. Okay, so that's basically it. That took longer than I thought. Again, let me know what you think. Let me know what you want to see. Could be a while before I'm back, but I will be back.